Good morning, everybody. Today we are moving on to discuss a new topic in our physics course. This is optics. And firstly, as always, you and I must understand. But what does the word optics mean? The term optics comes from the Greek language optos. Translation from Greek language, this is visible. Now, the very definition of what is optics and optics definition. Let's see. Optics is a branch of physics that studies the nature of light, the law of its propagation and interaction with matter. And questions about the nature of light and matter have a long history, but until a certain time it was believed that the answers to them must be unambiguous. Light is either a stream of particles or a wave. Matter either consists of individual particles that obey classical mechanics or is a continuous medium. For many centuries, physics could not come to one opinion about the nature of light. And in the 20th century, the general opinion was that light has a dual nature. The recognition of the dual wave particle nature of light was one of the greatest achievements of physics in the 20th century, really. We currently know that the light travels or propagates like as an electromagnetic wave, but light is emitted and absorbed as a particle stream. Its name are photons. I think you know this. And according to this dual nature, we can say that light has a wave corpuscle dualism. This is the main function, the main idea of light, the main idea of photons, that light is not simple. Light is complex system which consists of particles, photons, and it can propagate, it can go through the matter like an electromagnetic wave. Please don't forget about it. Now, let's discuss with you the main sections of optics. We can divide optics into three large sections. These are geometric optics, wave optics, and quantum optics. Let's start to talk about first part. First part is geometric optics. What is this? Geometric optics is a branch of optics that studies the laws of light propagation in transparent media, light reflection from mirror reflecting surfaces, and the principles of constructing images when light passes through the optical systems without taking into account its wave and quantum properties. Light here propagates as a geometric ray or spreads like as a geometric ray. What is about wave optics? Wave optics is a department of physical optics in which interference, diffraction, polarization, and other phenomena are studied for understanding which it's necessary and sufficient to understand the wave nature of light. We can say light spreads like an electromagnetic wave, how we said earlier. And the last part is quantum optics. What is about quantum optics? Quantum optics is a branch of optics that deals with the study of phenomena in which the quantum properties of light are manifested. We can say light is emitted and absorbed as a stream of photons. In our course, we will discuss the laws of geometric optics, especially without laws. We can't be without geometric laws, laws about in geometric optics, and partial wave optics, some definitions we can say. And in practical classes, we will discuss laser radiation. Laser radiation is a part of quantum optics, light amplification, stimulated emission by radiation, and perform laboratory work to determine the wavelength of the presented laser. It's very interesting laboratory work. I will show you the video with our laboratory work, and you will try to calculate to know the wavelength of laser and the color of laser. So let's take a look at the basic laws of geometric optics. We will start to discuss geometric optics, and we must start from the laws of geometric optics. We will be discussing 5 or maybe 6, we can say, basic laws of optics. The first law, which we will discuss, is the law of rectilinear light propagation. The second law is of independence of light beams. Next is the law of light reflection. And don't forget about the law of light refraction. And the last, very interesting and particular cases of law of refraction of light are partial and total internal reflection. It's very interesting part, and it's very necessary part for us for best understanding how can we use optics in medicine, especially in medicine, to diagnose different stages or different parts of organs in our patient, of our patient. So let's start to talk about laws. And firstly, the first law that we will discuss with you is the law of rectilinear light propagation of light. How can we say about this law? The light beam in a homogeneous transparent medium propagates in a straight line or propagates rectilinearly. Most importantly, the environment must be homogeneous, that is, the same in its properties throughout the discussed area of space. And then the light beam becomes the standard of a straight line as a geometric concept. A straight line is the shortest distance between 2 points, and the curvilinearity of light rays in an inhomogeneous medium is explained by their refraction and the boundaries of layers of a medium with unequal density. The proof or the evidence of this law is shadow or umbra formation. What is about umbra or what is about shadow? You can see it on the picture black part of this. So what is about? This is the area where light does not fall. We can see on this picture, on the skin. What happened? The light go like as a straight line, propagates like as a straight line, and we can take the object. And what happened? After this, on the wall, for example, we can see the shadow, the umbra. And this is the part and evidence of this law. And what is about umbra again? This is an area where light does not fall. Next is the law of independence of light rays. What is about light rays? Yeah, how can we explain this law? Light rays, after crossing, we can see on the picture, after crossing, don't change the properties of each other and don't change their direction. And we can say that light propagate independently of each other after crossing. The proof or the evidence of the law is formation of penumbra. You can see it. We can see two parts because let's see on the picture. We can take the object and what happened. On the wall, we can see not only umbra, like as in law of rectilinear light propagation. We can see two parts, deep shadow part and partial shadow part. What is about deep shadow? We said that this is the umbra, where lights can go fall, yeah? Don't fall. What is about penumbra or partial shadow, yeah? This is the area of a partial light hit, we can see. This part is umbra, this part is penumbra, we can see. This is the evidence of this law. And consider the following law that you all have known from childhood. We loved the sun and loved mirrors and take sun into mirrors and see it in the wall, for example. Yeah. So this is the law of reflection or law of light reflection. We see most of the objects of the surrounding world thanks to the light rays reflected from their surfaces. Less often you have to deal with objects that are themselves sources of light. The law of light reflection is valid for specular reflection of rays, and the reflected ray lies in the same plane as the incident ray and the normal reconstructed at the point of evidence, and the angle of reflection is equal to the angle of incidence. We can see in the picture that the incident ray, which come to surface, to mirror, for example, reflected ray, and the perpendicular lowered in to the point of incidence lie in the same plane. All rays lie in the same plane. So, what is about angles? We know that angle of incident, theta, eta, e. What is about incident angle? We can say alpha angle is equal to the angle of reflection, or we can say beta angle or theta r, yeah, reflected angle. But you can see that we must not take this angle between incident ray and surface. It's a mistake. We must take angle between incident ray and perpendicular to surface and reflected ray, between a reflected ray and perpendicular to surface. Please be careful with this and don't forget about it. And what is the next? After reflected, we know that must be refraction, yeah, refracted. But before moving on to the next law of optics, we need to discuss some important concepts. First of all, we'll talk to you about refraction. What does the concept of refraction of light mean in general? Refraction or refraction of light is the deviation of light from its original direction of propagation. This is a definition of refraction. When light passes from the one medium to another medium, the velocity or the speed of propagation of light changes. Therefore, the light is refracted. Let me remind you, the speed of light in vacuum is, I think you know this number, velocity of speed of light, velocity in vacuum is 3 multiplied on 10 to the power 8 meter per second. This is the speed of light in a vacuum. And further, we now understand what is refraction, but we also need to understand how does it happen in general, and is there any physical quantity that characterized it? Certainly, there is. And the first characteristic is the absolute refractive index, letter N. This is the dimensionless physical quantity that shows how many times the speed of light in a medium is less than the speed of light or velocity of light in a vacuum. So we can compare the medium, different medium, for example, air, for example, water, for example, our tea or coffee, and compare it with vacuum and say how much times can this medium change the speed of light. So when we compare it with vacuum, we know that vacuum is a medium, we can say, without molecules, like as a whole. So how can we calculate the absolute refractive index N? We should take speed of light in vacuum or velocity of light in vacuum and divide it by speed of light in environment or speed of light in medium, where we can put this light or where we can see this light. But this is only an explanation of the interaction with the vacuum. We compared vacuum and medium. For us, it's important to understand what happens when light passes from one medium to another. It's more interesting for us, For example, we are swimming in the sea, and sunlight can go through the air to water, and we can see objects or other inside of water, And what happened? We know that in water, objects which we can see, it's other, but it's like as a miracle. So let's say about other physical quantity that can say us understanding or explaining when we compare two different mediums. So this is relative refractive index. But when a ray passes from the one medium to another medium, the velocity of light changes. Really, you know this. I think you know it. Which leads to a turn of the front of the light wave and, accordingly, to a sharp change in direction. Refraction of light rays is perpendicular to the front of the wave. This describes to us the relative refractive index. You can see the letter, this is N, and N with index non-21. This index shows us from what medium to other medium, the direction of light's beam, from 2 to 1, so N to 1. So we know that the light spreads through the second medium to the first medium. So again, it's not 21. This is the direction of light's beam. So according to this, lights go from the second medium to the first medium. Maybe opposite, when light spreads from the first medium to the second medium, and the number was maybe n2, n1, 2. So this relative refractive index shows how many times the speed of light in one medium is less than in another. So let's see the formula, yeah? How can we calculate this index? We should put the absolute refractive index. We should divide absolute refractive index on the second medium, divide by first medium, because our direction we can see from the second to first. Maybe opposite, maybe from the first to second. Number will n1, 2, and we should divide n1 by n2. And we should compare it with velocity, because we know that velocity of light in different medium is different. So we should put it with opposite, yeah? If we divide n1 by n2, we must divide v1 by v2. And what is about v1 and v2 again? This is the speed of light in the first and the second medium, yeah, or environment. So this is relative refractive index. It was relative refractive index. Now we can move on to discussing the law of refraction. And what is about this law? This law is fulfilled when light passes from one transparent medium to another, and consists in the following: that incident ray, reflected ray, refracted ray, and the normal of the system lie in the same plane. Or we can say that refracted ray lies in the same plane with incident ray, and the normal restored at the point of incidence. And the ratio of the sine of the angle of this incidence, yeah, to the sine of the angle of refraction is a constant value called the relative refractive index of the second medium with respect to the first. And the diagrams, the picture, the scheme shows a variant of the passage of light beam from an optically less dense into an optically denser medium. So we can see that absolute refractive index of the first matter is less than the absolute refractive index of the second matter. How we can understand it? Yeah, because the incident angle is more than refracted angle. We can see it. And this is the Snell's law with the signs, yeah, of angles. And in this case, again, we see that the angle of refraction will be less than angle of incidence and vice versa, yeah, because we should compare refractive index, absolute refractive indexes of mediums, and according to this will be changed the velocity or speed of light in these mediums, and we can put it in Snell's law. It can describe us the dependence between matter and the sine of incident angle and the sine of refracted angle. Don't forget this law, please. It's very necessary for us. And for example, this case shows us when the light beam go from the air to water, for example, from air to water. And again, don't forget that N2 and N1, this is the absolute refractive index of mediums. And theta 1 in this law is the incident angle, theta 2 is the refracted angle. Don't forget about it. But this law has some exceptions. Let's take a look then. Consider the case when a light beam travels from an optically denser medium to an optically less dense medium. For example, from water to air. Let's see this situation. Opposite of this part. We go from water to air. Again, according this picture, this first picture. And imagine the situation that we are underwater and shine a flashlight on the surface. For example, what happens then? Everything is much more interesting here. For each medium, there is a special limiting angle of refraction at the interface between the two media. This corner is a kind of border. If you and I increase the angle of incidence of the light beam, and our angle of incidence becomes equal to the limiting angle for a given medium, then the angle of refraction in this case we also increase, and as a result will be equal to 90 degrees. So if we can change the incident angle, and we can what happened? We can change it, and how? We can increase this angle, and for different medium, for each medium, there is the special limited angle, like as a border, like as a border angle. What is this? This is a critical angle. We can see critical angle, limiting angle. When the situation, what? If the incident angle will be the same with the critical angle with this matter, what happened? The refracted angle will be 90 degrees. And the situation, what happened? The light beam can spread on the surface, on the border between mediums, or on the first surface on the second medium. What happened? The law of partial internal reflection, this is the law of partial internal reflection. That is, we can increase on our angle of incidence of the light beam from the flashlight to such an extent that the refracted beam will propagate over the surface of the liquid. I think you did it when you were in the sea, maybe, or in the swimming pool, maybe. You can do it if you can swim. Let's see on formulas of this angle. Partial internal reflection, this is a part of or special case of refraction. So what happened? We know the Snell's law to refraction, to refraction. So we know that our refracted angle is 90 degrees. And when we put it into formula and know that sine of 90 degrees is 1. And what happened after? How can we calculate this limited angle or critical angle or incident angle? How can we calculate it? We can put absolute refractive index of the second medium divide on the absolute refractive index of the first medium. That's all. This is a partial internal reflection when the Incident angle is the same with critical or limiting angle for this matter. And after that, the refracted angle will be 90 degrees. 90 degrees. So, and what happened? What happened? If you and I continue to increase the angle of incidence, so let's put that our angle, that our incident angle will be more than critical angle, for example, like here. What happened after? What happened after? Let's see. And in the case when the angle of incidence of a light beam on the interface between two media is greater than the limiting or critical angle of incidence for a given medium, then in this case there will be no refraction at all. There will be a total internal reflection, as in the law of reflection. Let's see again. Again, the situation when the light beam passes from a denser medium to a less dense medium, optical denser medium. So, if we put our incident angle more than critical angle for this medium, what happened after? Our refracted angle will be increased, and what happened? We will be a total internal reflection, as in the law of reflection. Refraction, no, only reflection, So let's see, in this picture we can see that the light beam go to the border between these mediums, and we can see total internal reflection. And in this total internal reflection, the angles is the same, We can see incident angle and reflected angle is the same, like as in the law of reflection. And the law of total internal reflection is widely used in our life, really. We can use it in our life. How? Where? And fiber optics are based on the phenomenon of this total internal reflection and are widely used in medicine. Where? In endoscopes. What is about endoscopes? These are devices for examining internal cavities. And the endoscope works on this physical phenomenon, which is used in diagnostic. Again, where? And what is consist of? The light guide, which a bundle of a large number of thin glass fibers placed in a common protective shells, is introduced into the cavity under study. Some of the fibers can be used to transmit laser radiation into the internal cavity for therapeutic purposes, for example, maybe, or light radiation, What happened? And however, fiber optics has a strong competitor in a field of endoscopy. Thin video endoscopes with a miniature video camera, like in this picture. This is a new endoscopes, and this is old endoscopes when doctors see into endoscope. But in this case, doctors see in the computer and see the video of the patient cavity. So, and are replacing thick fiber gastroscopes. This technique produced a much higher quality image. image. So, what else? One part of the fibers, we can use this endoscope on two different fibers, and one part of these fibers bring a beam of light to the organs, which being reflected from the surface of the organ and returns back along the other part of the fibers and is projected into the computer screen or the retina of the doctor's eye. And according to this, we can diagnose, we can see the patient's organs cavity, for example, stomach, for example, intestine, and for example, what? For example, bronchoscopy, and other cavities and other cavities for checking or for recognize the problem of patient, and after that we can help our patient. And not only see, we can't not only see, we can take what? We can take the part of organ, yeah? We can take the part of organ, and after that we can check the tissue, this tissue, and for example recognize the problem if because maybe the oncology or cancer, for example, of stomach or intestine. It's maybe, and according endoscopy, using endoscopy, we can check, we can check, recognize, and after that we can help our patient. We can help our patient. Having discussed the law of geometric optics, we will discuss with you one important concept from wave optics. Yeah, we discussed with you all main geometric laws of optics. Yeah. Now, let's continue and important concept from the wave optics. This is the dispersion of light. What is about the light dispersion? The light dispersion of is property of light of a complex composition to decay upon refraction into simple components, visually perceived as multicolored rays of close directions. Dispersion is explained by the fact that the refractive index of a substance is a function of the light wavelength. Light components with different wavelengths are refracted in different ways. Let's take a look at the picture on the slide, on this picture. And it depicts the simplest spectral instrument. This is the glass prism. We know that glass prism is the simplest spectral instrument or device. To the left of the glass prism is an incident sunbeam, or this is white light beam. Yeah? What happened? And on the right, on a vertical screen, a continuous spectrum of sunlight. Its visible part, yeah, this is the visible part. Colors range from red to purple or to violet. When passing through the prism, the light refracted twice, firstly and secondly. The decomposition of the sunbeam in the spectrum occurred at the first refraction, firstly. The second refraction led only to a slight increase in the angular divergence of the rays at the exit from the prism in the second part. Why it may be? Because the white light is complex, but these lights, red, orange, yellow, green, blue, indigo, violet, this is a simple lights. If we use a glass prism, we will divide only complex light. We can't divide the simple lights. Please be careful with this. Yeah, we can divide simple lights. Like if we put the prism here, what happened? We will see the same colors, but other angle, other refracted angle. That's all. That's all. And dispersion of light is also found in the surrounding life. One of the most beloved physical phenomena in nature for us is rainbow. Rainbow. And we see it as something wonderful. But in fact, this is an example of a natural phenomenon, the explanation of which is three phenomena that occurs together. This is the refraction of light, dispersion, and reflection of light. The first theory of the rainbow was proposed by the René Descartes. A rainbow occurs when the sun is somewhere behind you and its oblique rays illuminate rain clouds. In the smallest and therefore slowly settling raindrops, the following happens. Three main happens. Firstly, will be the refraction of sunlight on the surfaces of drops close to you, accompanied by its dispersion, like here. We can see refraction and dispersion. What after will be reflection of light, decomposed into a spectrum from the distant surface of drops. Let's see. This is the second. This is what? Reflection. Simple light, only reflection. And what happened after? Will be refraction of drops on the surfaces closest to you, with the release of multicolored rays towards you. Admiring eyes. Let's see. Firstly, what happened? Refraction and dispersion. Secondly, reflection. And thirdly, refraction of simple lights. And we can see the rainbow using our admiring eyes, like as a miracle, for us. But this is a simple physical phenomenon. Simple physical phenomenon, but is a complex physical phenomenon, which consists of the refraction, reflection, and dispersion. That's all. Only physics around us. So, we discussed with you the basic laws of optics, light dispersion. Now, we must move on to discussing lenses. The British Museum has a lens that is more than 3,000 years old. This plain or complex Rowley ground lens still archives in 3 times magnification. Our distant ancestors used similar lenses for making fire. Basically, we will be discussing lenses formed by spherical surfaces. One on the surface can be flat. A lens is, what is about lens? We can say the definition of lens. What is it? This is a transparent body bounded by 2 spherical surfaces, or a spherical surface and a plane, for example. And on the picture, you can see 2 different lenses, convex lens and concave, for example, lens, and converging lens, diverging lens. So let's continue. Lenses are converging positive and scattering negative. You can distinguish them by touch and even in the dark. If you take into account a general property, any lens deflects light toward a wider or thicker part. So, All collecting or all converging biconvex lenses in the center are thicker than at the edges, for example. And scattering ones, on the contrary, are thinner in the center, thicker at the periphery, if we compare it. So, we can say that there are two types of lenses, converging and diverging, diffusion maybe lenses. Let's watch a video with you on how our lenses work.
In today's video, we're going to take a look at lenses and see how they can focus and disperse light using refraction. We'll also cover the difference between real and virtual images and see how a lens's power changes with its curvature. Now, as we can see here, there are two main types of lenses, convex and concave. Convex lenses have an outwards bulge in the center, which causes them to refract parallel rays of light inwards to a single point, which we call the principal focus. Another name for a convex lens is a converging lens, because they cause the light rays to converge, which just means to come together. Concave lenses, on the other hand, cave in on either side, which causes them to refract parallel rays outwards, so effectively disperse the light. To figure out the direction that they'll be refracted in, we have to trace virtual lines from the lens's principal focus to where the rays hit the lens. And then if we continue these lines, it shows us where the real rays will go. Now, regardless of what type of lens it is, all lenses have a principal focus on both sides, and there will be equal distances from the center. So our convex lens would also have a principal focus over here, and the concave lens would also have one here. And also, you might sometimes hear the principal focus being called the focal point, but they're both exactly the same thing. Because they have a principal focus on both sides, lenses are basically symmetrical and can work both ways. So if we were to reverse the direction of the light, so that it's traveling from right to left, everything basically flips, and the light focuses on the opposite side of the lens. Another important thing about the principal focus is that it will always sit on the axis, which is this line passing through the middle of the lens. The distance between the principal focus and the very center of the lens is called the focal length. And the shorter the focal length is, the more powerful the lens will be, which just means that it will refract light more strongly. In order to make a lens more powerful, we need to either make it more curved or use a different material that naturally refracts light more strongly. The last thing we need to cover is the difference between real and virtual images, which, to be honest, is kind of a weird concept, so just bear with us and hopefully it'll make sense. Now, regardless of whether it's real or virtual, images are formed at points where all the light rays from a particular point on an object appear to come together. A real image, like we can see here, is formed when the light rays actually do come together to form the image. For example, these light rays from the chicken's head pass through the lens and converge in the bottom right, which is why we see the chicken's head down at the bottom. Meanwhile, the light rays from the feet converge in the top right, and so we see the feet at the top. And because it's a real image, if there was a screen here, then the image could be captured on the screen. To give you some idea of where this happens in real life, whenever you look at a real-life object, like a spanner, the light rays from that object pass through the lens in your eye and form a real image on your retina. And it is actually inverted, like this one here. We just don't notice it because our brain corrects it for us, so that everything appears to be the right way up. If we look at this diagram instead though, we're seeing a virtual image. Virtual images are formed when the light rays don't actually come together where the image appears to be. For example, in this case, these dashed lines aren't actually light rays. They're just virtual rays that we trace back from these points towards the focal point. So because these are only virtual rays, what we're forming is only a virtual image. The most common example of a virtual image is whenever you look in the mirror. The images you see aren't real images, because although the images appear to be behind the mirror, there can't really be any rays behind the mirror, because it's a solid object that light can't pass through. So they're only virtual rays forming a virtual image. Finally, when it comes to describing images in exams, as well as mentioning whether they are real or virtual, you also want to comment on whether the image is upright or inverted, and whether it's bigger or smaller than the object. So in our example on the left, the image would be real, inverted, and smaller than the object. Whereas in our example on the right, the image would be virtual, upright, and smaller. Anyway, that's everything for this video.
So, now you understood that in collecting or converging lenses, we can get both real and virtual images. And it all depends on where the item is. Let's take a look at the drawing on this slide. If the subject be between the main focus and lens, and what lens? Collecting lens, yeah? Or converging lens. We get an image enlarged, imaginary, or virtual, yeah? And direct. If the object is between the main focus and the double focus of the lens, then we can say only about converging lenses. The image is real, inverted, and larger than object, and farther from the lens than object. If we compare the distance between lens and image and the distance between lens and object. So, well, if the object is behind double focus, then the image in the collecting is real, in collecting lens is real, reduced, smaller than object, and inverted. And closer to less than object. You can see these rules. And as for diffusing lens, in the diffusing lens, we always get only a ghost or a virtual image, and it does not matter where the object is. So, some of you may be wearing glasses. For example, I wear glasses because I have problems with my eyes. And you may also be interested in the fact that all lenses in glasses are different. But what physical quantity can characterize them? This is the optical power of lens. Optical power P of a lens is a value, or physical quantity, that characterizes the refractive power of axisymmetric lenses and centered optical systems made of such lenses. The optical power of the collecting lenses or the converging lenses is always positive, and the optical power of the diverging lenses is negative. Don't forget about it. According this law, how can we calculate the optical power P? We should put 1 divided by focal length. Divide by focal length. And the STM International Unit is 1 divided by meter, because focal length is distance. But we can use the special non-STM International units for best understanding is diopter. Yeah, our glasses has a diopter. For example, my glasses is -2⁵ diopter. Both of my lenses in my glasses. So we have discussed with you quantitative concepts about the characteristics of image and in the lens, yeah, earlier. So, but physics is a quantitative science. Let's discuss the quantitative characteristics of the image in lenses. Let's take a look at the scene lens formula with you. A length is called scene if its thickness is many times smaller than the radius of curvature of the lens. Let's take a look at the diagram on the slide. We see with you a converging lens and an image in it on the picture. Converging lens, collecting lens. Let us denote with you the distance from object to the lens by letter what? D, small d, or to object, yeah? And the distance from the lens to image is d with index I, like as the image, distance to image, object, image. I1 is the object and I1 is the image. So the focal length of the lens is denoted by a small letter f. We can see it, yeah, small letter f is the focal length. We can prove this formula using the rule of similarity of triangles. From the similarity of the triangles obtained when constructing the path of the ray, a relation arises that connects the above parameters and is known as the formula for a scene lens. We can put 1 divided by focal length is equal 1 divided by distance to object plus 1 divided by distance to image. Don't forget, if we have a positive number of focal lengths, will be convex or collecting converging lens. If focal length is negative, so we will take concave, biconcave, collecting converging lens, yeah? Diverging lens. So the distance distance between object and lens always positive. Everything, everywhere, every time will be positive. And if we have the real image, yeah, distance between image and lens is positive, virtual image negative, this distance will be. So let's give an example of the application of this formula in the surrounding life, namely in medicine. Our eye is an optical device, complex optical device, and a very complex one. Let's imagine a model of our eye. Eye model is a reduced eye. What is about reduced eye? A model of a visual system which is a collecting lens equivalent in its refractive properties to the optical system of the eye. The scene lens formula is a mathematical description of this model. The eye model is a converging lens surrounded by air from the object space side and liquid from the image space side. For example, Around us there is air, and inside eye there is water, liquid. Yeah, liquid. The reduced eye is like as a single lens. One side is affecting the air, absolute refractive index of air is 1, and the other is a contact with the liquid. This absolute refractive index will be 1.336. So the left and right focal lengths are not the same, we can see, not the same. The front focal length f1 is 17 millimeters on average, and the back focal length is 23 millimeters. So let's compare this and this distance. So the optical center of the system is in the depth of the eye at a distance of 7.5 millimeter from the outer surface of the cornea. We can see this model. This is a scheme of our eye. Really, our eye is very complex system. And it consists of many different parts. And in physics, we must discuss only physical part, which we can use in physics for best understanding about our eye. And let's see. In our eye, there are two collecting lenses. This is the lens and vitreous body or vitreous humor. So, we must understand that the retinal image characteristics are: we can see all objects. How? They are real because our lens, our eye is a collecting lens. They are reduced, really reduced, and inverted images. We can see inverted images, and our brain, can change this image, and we can see normal objects like they are in our life. So, and as I told you earlier, our eye is a very complex system, really. And from the point of view of physics, it has two main parts of our eye. Let's see at the picture again. Our eye has a light receiving apparatus of eye. This is the retina. Green part is retina. What is this? This is it consists of nervous system, nervous cells, and this is the receptors of light. They can receive. They can't change the light. It can only receive the eye. So, what is the second part? The light conducting apparatus of the eye. And we must tell some words about a light conducting apparatus of the eye. It's represented by the following parts of eye. Let's see how the light can go through our eye. According red arrow or according this arrow. So, firstly, the light can meet what? Can meet the first part. The first part, outside part of our eye, this is the cornea. Cornea has the highest refractive power, and its optical power is plus 42.5 diopters. Yeah, so it is the first, and this is the part of what? Part of our eye, and after cornea, in cornea, light can refract, and after that go continue, where we can, light can meet what? This part. This is the anterior chamber of eye. And in anterior chamber, there is a fluid. There is the fluid. What happened? So it's the fluid. It can change the direction of light. So optical power of liquid in anterior chamber is from +2 to +4 diopters. So after this, lights meet the lens. Its optical power changes quite strongly, since thanks to the ciliary muscles, it's able to change its curvature and optical power from +12.5 to +33 diopters. We can see that the lens is the changing part, and ciliary body take the lens using ciliary muscles and zonular fibers. Ciliary muscles. Our muscles can contract or not contract, so the curvature can change of lens. So about this we will say later. So the last part of light guide apparatus, or light conducting system of eye is vitreous body. The biggest part of eye is vitreous body. It occupies the largest volume, and has an optical power, negative optical power, from -5 to -6 diopters. And after that, lights go to fovea, to retina, of retina. And after that, this is the light conducting part. Receptors can check the light, can check the energy, change it or translate it to action potential, connect to our brain according using nervous system, and after that we can see the objects in our life around us. So as I said earlier, the lens of the eye is able to change its curvature thanks to the ciliary muscles. Ciliary body take the lens using ciliary muscles. This ability is called accommodation. But what is the accommodation? Let's see the definition of accommodation. This is the eye's ability to clearly see variously distant objects. This is possible because due to contraction of the ciliary muscles, the lens can change its shape, that is, change the optical power. And you and I and other people can view objects at different distances. When you and I look into a distance, for example, and not of this, we know that all people can see all objects clearly, if it near to us, far from us, and other distance between object and our eye. So it may be according the special part of our organism. This is an accommodation. Don't forget about it. This is a special ability of our eye. And when people look into a distance, we feel that our eye seems to relax, and it's convenient for us to look into a distance. From the point of view of physics, this process is described by the concept of a distant or far point of accommodation. What is this? The far point of accommodation is determined by the distance from the eye to the object with completely relaxed ciliary muscles. Really, for our eye is more comfortable to see in distance, yeah? For example, in the window, for example, in horizon, and other is relaxed to our eye. Why it may it be? Because our ciliary muscles are relaxed. So, with normal vision, these points lie at infinity. That is, the muscles are completely relaxed when you look into a distance to horizon. The border of this point is horizon because we can't see after horizon, yeah? And now, on the contrary, when we examine with you the small parts of object carefully and closely, then we feel what? We feel that our eyes seem to be straining, yeah? And for example, if we see the object near to our eyes. And from the point of view of physics, this concept is called the near point of accommodation or closest point of accommodation. The closest point or near point of accommodation. This has a distance too, but distance from the object to the eye with the most tense muscles. They are contract. With a normal vision, this is from 10 to 12 to 20 centimeters, maybe 10, 20 centimeters. And with age, this distance increases. Why? Because our muscles can't contract the same if we are the old people, for example. And well, each person has a certain distance from eye to the object. And when it's convenient to examine small parts of object or read small text. For example, it's not comfortable for our eye to see near object, yeah, to see the smallest part of object or read books near our eye because our muscles of ciliary body are contract and it's not useful for our eye. After this, we can take the problems with our eye. And in the case, the most important thing in the absence of tension in the eyes. And there is the distance between eye and object, near distance. When we see object good and it's comfortable for our body. This concept is called best vision distance or the best viewing distance. The best viewing distance is the distance at which it's most convenient to view the details of objects or read small text. And with normal vision, this distance is nearly 25 centimeters. And for every people, it may different, but near this number. This is the best viewing distance when we can see the small text or smallest parts of object and our ciliary muscles contract but without pain in our eye, and it's comfortable for us. It's comfortable for us. The distance, comfortable distance to see small objects, small text, yeah, and other smallest part of bodies, of different bodies, of our body, of objects and other parts. And according this eye accommodation, yeah, according our ciliary muscles, according our form of our eye, it can change really. People can take problems with eyes. And firstly, we can see on schemes what is about eye accommodation on scheme. We see relaxed ciliary muscles are relaxed, and after that unaccommodated lens. And opposite, accommodated lens when the ciliary muscles are contracted and zonular fibers are relaxed opposite. So it's accommodated when we see the near objects of our eye. Let's see on the form of lens when we see on distance focus, or we see the close focus or near of eye in the form of the lens. So now let's say about visual impairment or about eye problems. There are three main eye problems which people can take when they use computers near the eye, telephones near the eye, especially in the dark. It's not good for us. Or use it when they lie on the bed, for example, yeah, and other situations. And we also know that there are many different types of vision pathologies, of eye pathologies. Let's take a look at some of the vision problems. Firstly is myopia. Other name is nearsightedness. So this defect is also called myopia, and it refers to visual impairment where a person can clearly see close objects, but distant objects are blurred. The defect is caused by lengthening of the eyeball or excessive curvature of the cornea. The defect can be corrected with a diffusion lens, which focuses the image on the retina. This is the myopia. I have a myopia. The next visual defect is presbyopia. What is about presbyopia? This defect is associated with the eye, the ability of which to focus object is reduced. And for example, people can say this problem that I can focus on the object, really. I cannot see near object, far object, because my eye is not focused. It's not comfortable for us, really, because we can't read the book, we can't read the text, we can't use the telephones, computer, and other. It's not comfortable for us, really. It's very bad problem. But with age, the force of accommodation decreases due to the weakening of the ciliary muscles. And these problems can be corrected with a bifocal lens. And the last one is hyperopia, which we can see on our lecture. This defect is also known as a farsightedness. It is the opposite of myopia and is a visual defect in which a person sees near object with blurry vision, but distant objects are clearly visible. A defect occurs when the eyeball is too short or focal length is too long. And this problem can be on old people, yeah, especially on our grandpas have this problem. because with the age the eyeball can change, and after that the people has problems like as a hyperopia. How can we correct this problem? The problem is eliminated by using a converging lens of the required focal length. All of these problems connect with the physical part, connect with the form of eyeball, connect with the cornea, connect with the lens, connect with the ciliary muscles, connect with the ciliary muscles and focused on image. So now I can say you thank you for the attention and see you on the next my lecture. Don't forget about lectures, and you must see this lecture and ask your teacher on practice lesson if you don't understand some material from lectures. Thank you for the attention again.